All right, this is actually really good because we're going to use this as a chance to kind of refresh. Go away, little box. I don't know why that box is there. All right, so let me just draw a really quick galvanic cell. And you guys should hopefully remember what those guys look like because Miss has gone through them. But I wasn't there for that lesson, so I'm not really sure what depth she went into it and also what you guys already kind of practice and know. So the thing with the galvanic cell is we're going to have two beakers. Do you remember why we need the two beakers? Two different solutions. The other thing I want to do is I want to separate my redox reaction so that way I have control over it because I want to basically decide the pathway that the electrons are going. So with current electricity, that is the movement of electrons in order for that to happen. So there's several different things we need for that to happen. And I'm doing the example that you should have hopefully done the other day. That's our little voltmeter. All right, and then we have some solutions. So I'm hoping you guys did the copper sulfate and the iron 2 nitrate example. So copper sulfate aqueous, and then the iron 2 nitrate. Does this ring a bell? No. Oh, both will be fine. All right, so we need the two different beakers because we're trying to do two different solutions. Do you guys remember what the electrodes will be made up of if we're looking at the solutions? If they're metal?
Yeah, so iron and copper.
Yeah, iron and copper. So if I was looking at that guy here, that would be an iron electrode. And if I was looking at this electrode here, it would be a copper electrode. And then what's that thing in the middle?
Salt bridge.
Salt bridge. Remember that salt bridge there is just to allow for ions to move. So that way we complete our circuit. So that's the general format. I won't go through it in a lot of detail because I'm mindful that you guys have already done this. And the important thing that I want to show you guys is the standard cell diagram. All right. So did Miss cover how you figure out which is the oxidation and which is the reduction? A little bit. Okay. Shall I go over it? Because you guys would appreciate that. Okay. So we use our handy dandy resource sheet that you guys will be given on the assessment. I've made a few more copies if anybody needs a copy of it because they lost it. Unfortunately, it's not orange paper. I have it right, but anybody else need this? Standard reduction potential. All right. It was an orange piece of paper that helps if you find it. There's a lot of orange pieces of paper. All right. It's not the pretty orange color, but it'll do. Okay. So what you're going to do is you're going to look on this sheet for the two things that are in that galvanic cell. So I'm looking at the pairing. The first pairing I'm looking for is iron and iron 2. So the metal iron with the iron 2, which I can find here. Like that. I'm just going to circle it so we know where it is. The second thing we are looking for is the copper and the copper 2 ion. Do you guys understand how or why I know I'm looking for those two things? Yeah, so it just has to do with what's in solution and also what metal electrode I have. All right. Next thing I need to do is decide which one's the reduction and which one's the oxidation one. The way I do that is really simple. I'm using what is called the standard reduction potential. Everybody has been assigned a number. The higher the number you are, the easier you are to reduce. And remember, this is a spontaneous reaction, so it's going to go in the direction that we expect. So looking at these two numbers, the higher of the two is the copper 2 and the copper pair. So since that one's higher, that's going to be my reduction reaction. So if we go back to our notes, let's actually copy down those numbers. This one is positive 0.34 volts. This one is negative 0.44 volts. So this one here is my bigger number. So that makes this one the reduction reaction. And this has my oxidation. And that's how I figured that one out. She didn't tell you that? Well, I'm telling you guys that today. She might have held off on telling you guys that because you're going to use it later for a calculation. And so she could have been holding off to tell you that later. I'm telling you guys that because I think it's useful to know so you can identify which one's which. All right. Are we okay with that so far? Okay. Standard cell diagram is basically a shorthand way for me to write this drawing. So it's very common that you'll see it in questions because it means that when you write up the question, it doesn't need to be as long. You can just give it a shorthand. So what you are going to do is you are going to start with the electrode, and you're starting with the electrode that is for the oxidation half of the reaction. The way I like to think about how I write the standard cell diagram is where is the electron coming from and where is the electron going. So starting from the oxidation half, I would be here with my iron, and I would have my iron going from the solid iron to iron 2, because that's my oxidation reaction. So I write Fe, I write it as solid. This is how I'm starting my standard cell diagram. Once I have the electrode noted, we do a solid line. So that means electrode, now I'm talking about the solution. In this solution, we're only concerned about what's doing the redox process. So in this case, it is the iron 2. And that is my aqueous. Are you okay with that so far? All right. So that's my first beaker, is basically what that's showing me. Then I'm going to do 2 lines, and I'm just changing colors just to help you guys kind of see the different sections of it. You don't obviously need to do multiple colors. These 2 lines here are representing that I am now shifting to the other beaker. So when I go to that other beaker and I'm looking at this, this is my oxidation reaction. This one here has lost electrons. Who's going to be gaining those electrons? The copper, but specifically what copper? Is it the copper metal or the copper ion? The ion. So I'm going to write Cu2+, and that is aqueous, because we're talking about solution. So that's where my electron is gone. Again, you don't need to write all this extra stuff. We're just mainly concerned about the standard cell diagram. All right. And then what's my electrode? Cu, solid. So that is my reduction half. And that's what a standard cell diagram looks like. So when you guys are looking at questions, sometimes you'll have questions where all they will write is this component here, and they'll write the electrode, the ion in solution that's being oxidized, the 2 lines, the ion in solution that's being reduced, and then the electrode. So it's a real quick, short way for us to write basically this diagram. All right, some things that you guys need to keep in mind when you are writing. I just want to point out some stuff just to make sure you guys have all the different details, because I haven't had a chance to check in with Ms. Mudford to see what you guys covered. When you guys are looking at these things, it's very similar to what you guys were doing at the beginning when we're talking about justifying what we're seeing. So stating things like how oxidation number has changed, stating which one's the oxidation and why, stating the electron transfer, providing half equations, that sort of thing should all be going into your justification. The other thing that I find that most students trip up on is that they don't have the detail in what's happening with the observations linked to what's the specific thing making those changes. So for example, if I have my iron becoming iron 2, what should I expect happening to that electrode? Should be getting bigger or smaller? It's degrading. So you can obviously draw that on the diagram, but what you should be writing at is that this guy here is losing mass. And that's because it's becoming iron 2. The other thing you should be noting when you're stating your observations is not only what's happening to the electrodes, but what's happening in the solution. Is it becoming darker? Is it becoming lighter? Is it, what color is it? So in this case, I would expect it to become more pale green. So always talk about the electrodes, always talk about the solution. All right, on the flip side, I am going from copper 2 to solid copper. So what should I expect happening to the solution? Will it become darker or lighter? If the copper 2 ion is going to the copper metal. Lighter. So I would write down it'd be less blue. Or you could say that it's going lighter. And that's because that copper ion is getting reduced to the copper metal. What do we expect with the copper electrode? More mass or less mass? More mass. So gaining, whoopsie, that's a weirdo. Got 2 letters there, gaining mass. So I am happy with however you guys want to communicate your knowledge across. I'm happy if you guys are drawing the diagram and you're making notes on the diagram of what's happening, like you're showing me that that's gaining mass. I'm also happy if you want to write things down and just kind of annotate them. Make sure you are linking, though, and explaining why. So gaining mass, becoming lighter blue, this is both because we have the iron 2 going into copper. So that's the reasoning to why it's going from light blue and that electrode's gaining mass. Again, same thing with this one. Link it in for the because. So that's because we have the iron being converted into iron 2. All right, so just be mindful that you're stating your observations and you're stating the why behind your observations. All right, are we okay with that so far? Can I move it? Actually, the next question is, do you guys want a little bit of a break? Or shall I keep going? I don't know. Just take a minute, chit chat. Or keep going. Just keep going. All right, can I move it? Start a little fight club. That's what you guys can do. All right, let me show you guys another example. So this one has to do with inert electrodes. So again, we have the salt bridge. Again, we have our electrodes. So you're saying you guys like this one better.
It's easier, the hot equations are much simpler. Oh, from what she gave us.
Yeah, probably. I don't know. I also think that this one seems easier because you guys have done a question. Like you've done some of the content already.
Yeah.
Anyway.
But then she said there's an extra equation, so we were like, oh, maybe it's not.
There is an extra equation. Yeah. All right, I'm just going to do some solutions, and I like to do them in different colors so that way we can annotate what's what. Do this guy. Okay. So the first thing I want to kind of keep in mind is what do we have in our solution? So in this beaker over here, I'm going to give you potassium iodide. And this beaker over here, I'm going to give you potassium permanganate. So those are my solutions. They're obviously aqueous because we're only going to deal with aqueous in this case. The next question, actually, let's not skip to the next question. Let's go look at our resource sheet and figure out which one's oxidation and which one's reduction. So first off, do you think potassium's going to be involved in this? Nah, probably not. It's a spectator. It's at the bottom of my list here. It's very reactive, so if it was there, it was going to react with the water. All right, so we're going to look for iodine, and we're going to look for permanganate. So iodine's over here, I minus, with the I2. And then we see permanganate is looking for MnO4. I think that must be a typo.
MnO4 minus?
Yeah, we want MnO4 minus, and we want this one. And yeah. You also see it down here, but I don't know if that's a typo or mistake because that looks like it is a typo. Anyway, these are the two we're going to look at. So looking at this information, which one's oxidation, which one's reduction? The one that's higher. So this one here is my reduction. We're going from NnO4 minus to Mn2 plus. And then the iodide is going to be my oxidation. And that's going to go from I minus to I2. Let me make a note on the direction that we're going. So be mindful that since this is a reduction and this one's going forward, MnO4 minus to Mn2, this one is my oxidation, so it's going to go in reverse. Thus, I'm starting with the I minus to I2. So we should always have one on each side. Okay. All right, so now that we've done that, my next question is, what do you think our electrodes are going to be made out of?
Are they both reactive? Oh, wait.
If both, no, that's a good point. So, first off, what's the problem with potassium if I use it as an electrode? It's really reactive, so that won't work. It's going to react with the water. Manganese is what some people might be thinking. But again, that's not involved in the redox reaction, so it wouldn't be beneficial to use that sort of metal electrode. And now we come into inert electrodes. So these two here are examples of inert electrodes. So inert, do you guys ever heard that word before?
No.
Inert. So inert means unreactive. Which is what we want in this case, because we don't want this involved in the redox reaction. We want something that's going to be just kind of there to allow for electron transfer and to conduct electricity, but not actually take part in either of these two reactions. So two different choices you have for that. Do you guys remember what? One starts with a C.
Oh, wait.
Carbon. So carbon, the other one is platinum. Yeah, so carbon can also be referred to as graphite.
Oh.
Carbon is a type of graphite. We okay? The yellow. The orange, inert. I-N-E-R-T, inert. It means unreactive. So we use something like carbon or we use something like platinum. The other reason why we're going to be using this is, so these are both carbon electrodes. And we choose carbon, or I should say we choose graphite because we know graphite can conduct electricity. It's unreactive. The other thing we need to also look at is the phases of these guys. So in this case, we have the permanganate, which is aqueous, and the manganese ion, which is also aqueous. And then we have iodide, which is aqueous as well. And iodine, which I think on my list I have listed as solid. Oh, no, I have it listed as aqueous. It depends on what you're reading. You could have aqueous. So do we see a problem here? There's no solid. And even if there was a solid, like let's say I had solid iodine, would iodine be conductive? No. So you see what these are the reasons why we're using an inert electrode. So that's the other reason. States aren't solid. Or the solid version is not conductive or too reactive. Move that up. So we good with that so far? Make sense? All right, let's do then the standard cell diagram for it. I won't bother going through the observations and the equations because you guys can do that on your own. I just want to make sure that you guys understand why we're using inert electrodes and how to do the standard cell diagram. So when you have something like this and you have inert electrodes, the standard cell diagram changes ever so slightly, but it's nothing major. It'll still look very similar to what you guys were doing before. So I should start with the oxidation reaction, which is going to be this half. And I'm going to start with the electrode like I normally do. So my electrode in this case is carbon. So I will actually note that I have a carbon electrode. I then do a line to represent, now I'm talking about the solution in the beaker. And in this case, this is where the reaction is going to be listed. So we do the exact same thing. Where are the electrons coming from? Where are they going to go? What's being produced? So the electrons are coming from my iodine. That is aqueous. And then I'm going to do a little comma to represent that I'm talking about the other component in my reaction. So in the previous one, the electrode was involved in the redox reaction, so that's where we showed it. In this case, we're showing it within the solution. So that iodide is becoming iodine, and that one's also aqueous. So that's the only thing. It just shifts everything down a little bit. All right, let's then do my two lines representing I'm changing beakers, talking about the other component there. Again, we do the same thing. So this is what has given the electron. Now we talk about what has accepted the electron. So that's the permanganate, which is aqueous. And then again, do a little comma to represent what it's becoming, Mn2+, also aqueous. And then line, talk about the last electrode. So again, same sort of setup. This half is my oxidation. This half is my reduction. And I'm seeing where the electrons are going. It's going from here to there. Cool. So it's basically the order that you're putting it in. You're telling the story of where is the electron coming from, where is it going, what's going to be made when it loses that electron. That's it. So with that information, like I said, it's the shorthand of us trying to communicate across what the galvanic cell looks like. It's very common that you could have questions listed in the ESA guide or the SciPad that have this set up. So that way they don't have to write out all the details and explain which is the oxidation and which is the reduction. You can tell by looking at it which one's which. Cool. All right, that's me. What questions do you have? Yeah, so when it comes to the assessment, what I'm looking for is your depth of understanding for redox. And one of the ways you're going to show that depth is by writing the standard cell equations. That shows that you understand what's going on. It's also a good way for you to annotate as well if you want to annotate any changes and explain what's going on. And like I said, you can write and scribble all over the piece of paper. You can get some refill. I'm not expecting paragraph write-ups. I'm expecting annotations and things like that. Just still make sure you're using the word because and stuff like that, so that way you're showing me how you know what's going on. Cool. All right. Shall I move over to the Mahi choice so you guys know what you can work on? Okay.